Hello everyone and welcome back to another episode of the Hidden Quantum Champions. If you haven't subscribed yet to the channel, please make sure to subscribe if you want to check out and you don't want to miss on another one of these videos here, because I see that a lot of people are actually watching the videos but they don't really subscribe to the channel. So that would help us a lot in democratizing the knowledge and the accessibility of quantum technology, and it will help you to not miss out on another episode. But now let's hop right into today's video. Today we are looking at a company called Keysight or Keysight Technologies. So here we are on their website, and on the first look this might not seem to you like a typical quantum technology company, right? So it says hidden power of the SMU, source meter units can optimize dozens of tests, design emulation and test solutions to connect and secure the world. You see a lot of instruments here, so oscilloscopes, spectrum analyzer, signal generators, and so on. So on the first look, that doesn't seem like the typical quantum company. But if you have worked in a quantum computing lab before, especially in the solid state area, or if you have been doing any type of signal processing on small devices, Keysight might be a company that you've heard of. And in order to actually find out what they can do in the quantum area, let's quickly explore the solutions tab, because if we scroll down here, we see that there is something about quantum. So let's click on that and see what we can learn here. So it says quantum solutions, design and control quantum systems, from quantum device design and control to error characterization and scalable system integration. Keysight's quantum solutions reduce experimental complexity, accelerate development cycles, and equip researchers and engineers with the tools needed to scale from prototype to practical quantum systems. And then we see here quantum technology drivers, qubits, PQC, error correction, system design, quantum control, and quantum chips. Then here in Explore Quantum Solutions, we see three different categories. So there's quantum design, quantum control, and post-quantum cryptography. Let's quickly check out each single one of them. So here in the quantum design, it says accelerate design of superconducting quantum systems, streamline workflows, accelerate the development of quantum chips, and fine-tune quantum circuits. Quantum Pro EDA, accelerate quantum device development and enable accurate simulations, automated design optimization, and reduced resilience on costly physical prototyping. Then we have quantum design and layout, accelerate development cycles with a comprehensive design environment that combines circuit analysis, layout, electromagnetic simulation, and quantum extraction in one workflow. And then there's a superconducting qubit design, streamline the design, analysis, and optimization of superconducting qubits efficiently and accelerate development cycles. There is more, I think. So there's the last one here, quantum system analysis, enhance quantum workflows by simulating the time dynamics of quantum chips and accelerate the development of quantum systems. So that is very much a software stack, I think, which helps you to design and then also to analyze and to simulate those those qubits basically based on superconducting technology. So this is all for superconducting quantum bit systems. And you see these meander structures here that are then being fabricated onto the chip and then being used to create transmon qubits, for example. I would assume that. And it even helps you to fine-tune those circuits. Then there's the quantum control part. So here it says streamline quantum experiments, engineer and scale quantum systems with control and measurement solutions designed for quantum from the ground up. So there's the quantum control system, accelerate quantum algorithm development and system calibration with fast, precise, and scalable qubit control with low latency feedback. Then there's the quantum lab control software, streamline quantum experiments and accelerate results with specialized software focused on instrument control and lab automation for quantum applications. And then there's the quantum benchmark software, optimize your quantum computing platform through comprehensive error diagnostics, error suppression, and mitigation techniques. So it starts with the hardware, right? So here you have the control box with all the different connectors that then go to your cryostat, where inside you are hosting your superconductive system, right? This, I guess, comes with all the types of signal processing, as in like signal generation, and then probably also signal analysis that you need in order to do those superconducting qubit manipulation and measurements. Then you see the lab control software. So this is what goes onto your computer in the laboratory, and that controls, for example, this quantum control box, but maybe also the oscilloscope, signal generators, whatever you actually need. So, and I guess that kind of embeds everything that you can buy from Keysight at least. And then you have the quantum benchmark software, which basically takes the data that is being acquired via this quantum lab control software and analyzes it and actually helps you to gain some insight from that. And here it also says error suppression and mitigation techniques. So you can even feed back this information into the generation of these signals and so on, so that you have a better performing quantum system. For that, you actually need quite a lot of understanding of how the whole quantum system, of course, works, right? And then there's the post-quantum cryptography. This is now going into a different direction. So what we saw before was very much on the quantum information part, so quantum computing, generating signals, analyzing those, using those to improve your performance of the quantum system. This one here is now on a different part. So this is going on the cryptography part, where like quantum computers can crack existing cryptography schemes. There is one idea to use quantum technology to create a safer cryptography, and I guess that's what this goes into. So let's see: improve device security for the post-quantum era, address vulnerabilities and verify secure implementation of post-quantum cryptography (PQC) algorithms at each stage of product development. So pre-silicon side channel analysis, identify and fix hardware vulnerabilities in the design circle and verify that products are secure against threats posed by post-quantum cryptography, PQC. And then PQC security services, ensure secure PQC implementation with a guidance support and advice on mitigation strategies from Keysight PQC security experts. Yeah, so this is very much targeting this post-quantum cryptography era, where you want to make sure that your systems are safe against a hack with a quantum computer. Okay, then there's something on the use cases here. So what are the use cases that they're actually targeting? Number one, how to bias multiple qubits, minimize bias voltage fluctuations to prevent qubit decoherence. Then next one, application note here, designing for superconducting qubit circuits, build, analyze, and create fabrication blueprints for simple quantum computing circuits. There's another application note here, how to characterize superconducting qubits, efficiently characterize the quantum coherence properties of transmon qubits. So as I said before, transmon superconducting, right? Overcome DC bias supply challenges in quantum computing, DC biasing for qubits in quantum control and evaluation systems. And then an application note on calculate the CPW resonator properties, calculate the main characteristics of coplanar waveguide CPW transmission lines using the given quantum technology file. Okay. And then there's some more here: discover quantum resources, see more quantum resources, navigating the quantum revolution. So I guess that's more like, it says here it's a white paper. Successful quantum strategies employ problem identification and finding specific business challenges where quantum approaches offer clear advantage. Then there's the Quantum Technology Learning Hub here, curated collection of resources from Keysight engineers to deepen your understanding of quantum. And that's of course something that we like to see here very much. So again, a company that is helping you to make a first step into the world of quantum technology by offering some learning material here on their Learning Hub. There's another white paper here which says post-quantum key encapsulation, post-quantum cryptography in embedded systems with a focus on key encapsulation mechanisms. Then there's a flyer here on quantum control systems, direct digital conversion for microwave signals, eliminating common sources of drift and prevents frequent recalibration. And there's also a bootcamp, how to build a superconducting quantum computer, design, deploy, and characterize superconducting qubits with expert guidance. And then, there's some more here. You can book a demo or a meeting with the experts to learn more about the solutions that they have. Now, I think let's quickly hop into one of these use cases here, or into this specific use case, and see what Keysight is actually providing in terms of solutions for this multiple qubit system. So, how to bias multiple qubits? Minimizing bias voltage fluctuations to prevent decoherence. Bias voltage fluctuation, why is this important? Because if you have, for example, a quantum system, you need those gates in case of a superconductor, you have some DC, so direct current applied to the system. So DC is basically a stable voltage level or a stable current level, which has to remain stable over a long time, like the calculation time of your system. And if you start to fluctuate this, so if, for example, you want to apply 2 nanoampere, and now you have a lot of noise in there, that might actually cause your qubit system to do something uncontrolled. It might create some fluctuations. It might tune your gate. It might tune your flux. It creates, so a current again creates a magnetic field, right? And this magnetic flux, which is caused by this magnetic field, then again has an impact on your quantum system. And if this is changing over time, then of course you're also manipulating your qubit system, and that's what creates decoherence, for example, in your system. So therefore you want to make sure that these things are stable, these settings are stable, so that when you say this is like a direct current, it should always, so if you say it should be, 10 nanoamps, then it should stay at 10 nanoamps. And I guess that's the idea here. You see it goes into superconducting qubits and spin qubits. Let's quickly read through this. So characterizing qubit properties requires precise control and evaluation systems to initialize control and read qubits. The system enables the characterization of qubit properties such as decoherence, time, and fidelity while maintaining the integrity of the qubits. The DC voltage bias source is one of the most critical aspects in the qubit control and evaluation system for flux-tunable superconducting qubits and silicon spin qubits. Using low noise power supplies, source meters, and source measurement units (SMUs) are essential for minimizing bias voltage fluctuations. The clean bias voltage position must be as close as possible to the cryostat to maintain the integrity of qubit states, ensuring accurate and reliable quantum information processing. This approach can significantly help with unnecessary environmental interference caused by exposed cable length. Using a high-precision source measure unit and a low-noise filter can further minimize voltage noise. Employing different grounds for each instrument can create a circuit known as ground loop, which can be source of noise. Techniques such as single-point grounding are necessary to avoid ground loops. Experiments with the LF terminal configuration, such as floating or frame grounding, to understand the impact of the noise level of the DC bias voltage. Choose the one that yields better results. Noise from electromagnetic introduction can occur if the high frequency HF and low frequency LF cables become spatially separated. Keep the HF and LF cables as close as possible, or use a twisted pair configuration to prevent this from occurring. So there's a lot of signal processing knowledge in this paragraph here. It includes things that might not, let's say, be in the key focus if you look at a Keysight instrument, like for example these ground loops, but they play a crucial role in actually creating a clean measurement environment which you actually need. So you want to put, let's say, the measurement units close to the cryostat, so you don't have like 20-meter long cables running through your whole lab, because every cable can also collect noise on its way, so the signals can get disturbed. Then the other thing is this ground loop idea. Like if you have, for example, in the lab that I used to work in, we had separate systems, which was for like all the pumps and everything that draws a lot of power. Like if you have a compressor for a helium refrigerator, or if you have a turbo pump for the vacuum to be created, things like this. They draw a lot of power, and they also don't have a very flat power consumption curve, right? So if you, for example, turn on the pump, then it needs to spin up. It draws a lot of power, and then once it reaches its stable level, it might not be like that anymore. There's stuff which creates spikes in your network, and all of that creates noise, which then is partially flattened out by the measurement units themselves. So they have some filters in there, but you cannot filter everything out because you cannot accommodate for all of the different cases. So that's why you want to have, let's say, separate connections, separate networks, power networks for all of the measurement electronics, and then for the let's say other stuff that you need in the lab. Now, that alone is not enough. You also need to avoid these ground loops that they are talking about here. So if you have, for example, a lot of devices and they all have a ground connection, you might end up creating loops where like you have your central grounding here, and then you have one device which is grounded like this, the next one that is grounded like this, and there might be a connection between those two grounds, and then you create like a loop. And now this loop, if you apply a magnetic field, and in the lab, for example, you have magnets that are ramping up to 10 Tesla that do create magnetic fields, changing magnetic fields, you will induce some current in this ground loop, and thereby you will shift the potentials between the different grounds. And that can be an issue because now you think that in your qubit system, you have like two levels that are both the same level, but in fact they have a slightly different potential now because there's a current running in this ground loop, and that will cause a current running in your nanoscale system, and that can create either like a big problem, as in, okay, you destroy the whole system if the difference in the voltage is high enough, you will basically just blow up everything. But that's not what usually happens. What usually happens is you create a small potential shift, and that's already enough to kind of bias your whole system and create issues along that side. So you see, if you're reading through this, there's a lot of knowledge in there, partially targeted towards the signal processing, as in like where you place the device, how you where you place the device, which devices you need, and so on. But also very practical stuff like these ground loops. There's also something about twisted pairs here. So this is like how to set up everything around those systems. Another thing to mention that is also relevant in the bigger context is if you're looking at what is being done in research right now, you see that as the number of qubits is scaling up in those systems, like superconducting systems, but also spin qubit systems, other systems that require low temperatures, you see that there is a movement towards bringing stuff that is doing the signal processing into the cryostat. So before, we used to have these general purpose cryostats. You can do all types of experiments in there. You might have one time a sample in there where you do, I don't know, quantum qubit tests. The next day you put another sample in there where you do magnetic field and magnetoresistance measurements. So basically you have these all-purpose systems. Then at some point it became more specialized because now you had systems which have a lot of radio frequency lines going down. They're targeted toward one specific case, like for example superconducting qubits. You might not need a magnet anymore, so the magnet has been removed and things like this, right? Now, as the number scales up, the number of signal lines that go down to the chip have to scale up. And this is a problem because with every signal line that you draw down to the lowest stage of your cryostat, you also introduce another source of heat, because every line is an electric connection, and every electric connection can carry heat. So there's a limit which you can reach, and if you are reaching this limit, your cooling power of the system is not strong enough anymore. Of course, now you can make a bigger system, more cooling power and so on. And this is what we've seen over the last maybe 10 years, that cryostats have gotten bigger. You could buy more powerful ones, but at some point this will reach a limit again. And the limit is here probably not in how many qubits you can put on a chip. You can make the chip even larger and larger. And you can also draw more connections in there, but then you run into this temperature issue. So part of the electronics goes also down into the cryostat, and I think this is not something that is specific, like something that Keysight is looking into, but it's something to keep in the back of your mind. Still, I think these instruments here, they are very important. When I was working in the lab, I've also been working with some of those, so there's maybe also certain bias of myself. And they're very useful because they come with various different API connections. They're well integrated into various different lab automation frameworks. They have a very high quality, so they can measure really precise currents and voltages. Usually for me it was voltages. So I think they're very helpful instruments. But just to say, so there's this little movement also moving stuff into the fridge itself. Let's move on the website. Quantum qubit control solution, so providing stable and clean DC bias voltage to more than 100 qubits requires a combination of source meter options with a high channel density, low noise, and precision voltage supply. The Keysight quantum qubit control solution integrates 100 precise power supply channels in a 5U height of the full rack width space. The solution enables positioning near the cryostat due to its compact form factor, requiring qubit decoherence from environmental inference due to long exposure cables. This platform includes low noise filter adapters, LNF, to push the stability of the bias voltage further. So this is for the quantum gates, right? There's also a video here demonstrating that. And then explore products in quantum qubit control solution. So we also see other products here like this high density precision SMU. Then there's a low noise filter adapter here. And then there's also some software in here. And I mean, there's more products down here. And as you've also seen in the previous slide here, there's more articles to read through. But yeah, basically that should be it for today's video. I just wanted to show you that companies like Keysight, who might not be on your radar initially when you look at quantum computing companies or quantum technology companies, they play a very crucial role, because in most of the labs that are actually working on this on an academic side, and probably also on the industrial side nowadays, they are an important part of the solution as well. I could also imagine that the integrators that build the whole quantum system, they also usually integrate stuff into their system. Like they integrate they have suppliers that supply them with one specific thing, like for example the cryostat. I could imagine that also Keysight is playing a role here in supplying to a lot of companies the precision electronics, the measurement electronics that you actually need to run those experiments. With that, I think it's already everything for today's video. I hope you liked it. And as always, make sure to stay hydrated and see you in the next one. Bye bye.